If you want to start creating 3D content on your web pages and you don't know how or where to begin, you're on the right place, because in this tutorial I'll help you to get a good grasp of the fundamental parts of the widely known 3D library Three.js. This is by far the most downloaded 3D library, as it is commonly used by professional devs around the world to create 3D interactive content in browser games with almost 400k downloads weekly on npm. Before we start, make sure to watch the previous video if you don't know what is WebGL or what is the relationship between it in Three.js, link in the description below. And without any further ado, let's get started. The first thing we need to do is to create the projects folder in its package file. Then we are going to install a bundler. Using a bundler is not mandatory, but I highly suggest you to do so because it makes the project's organization way cleaner and easier to maintain in the long run. The bundler I'm going to install is Parcel 2, which requires zero configuration, but keep in mind that you could face a few problems with this version. I've used it here to make the tutorial as future-proof as possible. If you want to use a more stable release though, you can install the previous version, or maybe use a different bundler like Webpack. That said, to install Parcel 2, you can either do it only for this project by typing the following command: npm install parcel-save-dev, or install it globally to be able to use it in any other project without having to install it another time by typing this command instead: npm install parcel-g. The installation will take some time, so let's do other things in the meantime. First, let's create a source folder which will contain the app development assets like the images, HTML, JavaScript, and 3D files. Something important to keep in mind is that we need to use the type attribute and set its value to module if we know we are going to use the import statement in the JavaScript file we are linking to. So since I know we are going to do that, I'm adding it here. If you chose to use the version 1 of Parcel, this will generate an error, so don't add it. Now that our project files are ready, let's install Three.js by typing the following command: npm install 3. That done, let's type some code. First and foremost, we need to create a namespace, and let's name it 3 and import everything into it. Then we need to create an instance of the WebGL renderer. You can think of the renderer as a tool that Three.js uses to allocate a space on a web page where we can add and animate all of the 3D stuff that we are going to make later on. Having said that, to set the size of that space, we need to call the setSize method and pass the width and height as arguments. And here I want that space to take all over the page by using the window inner width and height properties. The next thing we need to do is to inject that space we've just created, which is basically a canvas element, into the page. Now we need to type the following command in order to make Parcel bundle the files and refresh the page automatically whenever we save any update in our code. Notice that a dist folder has been created the moment I pressed enter, and that folder will hold the distribution version of the app, including any asset that is located in the src folder and used in the code. To see the result of the few lines we typed, I'll push Ctrl plus left click on the URL provided by the server that Parcel has started. And there we go, we got our canvas ready. However, notice that we have some unwanted scrollable vertical and horizontal space, which is added by default by Chrome. To get rid of it, we need to set the CSS margin of the body element to 0. Before we continue with code, let's understand how Three.js works. First, when we talk about 3D in general, we are actually referring to a coordinate system composed of 3 axes. Furthermore, we get values from these axes to define the coordinates, aka location of a point in the 3D space. The first axis is known as the x-axis, and it represents the horizontal placement of a point on the graph. The left side contains negative values, while the right side contains positive values. The second axis is known as the y-axis, and it represents the vertical placement of a point on the graph. The bottom side contains negative values, while the top side contains positive values. The third axis is known as the z-axis, and it represents depth. Going from 0 to the front means negative values, while going backward from 0 means positive values. So again, that's how 3D works in general. It's not something specific to Three.js. Now let's talk about placing elements on the HTML canvas in Three.js, and let's begin with a simple analogy. Say we want to record a show. Obviously we need the right place where to record, aka the scene. We also need a camera. Then we need to add the components after preparing them outside the scene. And what I mean by components here is the lights, scenes, objects, and the actors. And what I mean by preparations is to choose the right lens for the camera and the right objects for the background, etc. These exact same things need to be done using Three.js. We need to have a scene by creating an instance of the scene class. Then we need to choose the right type of camera and create an instance of it. We have two types, and I'll get back to this subject in a moment. Once these two essential parts are ready, we can then introduce elements to the scene. Now back to cameras. As I said, there are two types of them. The first type is referred to as perspective camera. It is basically the same as real-life cameras. To create a perspective camera in Three.js, we need four values. The first one is the vertical field of view. It is the maximum angle of what can be seen through the lens of the camera. The second value is the aspect ratio. This one represents the proportion of the width and height of the image captured by the camera, and it is usually calculated by dividing the canvas width by the canvas height. The near and far clipping planes, these two represent the bounds of what can be seen and thus rendered. Anything in the scene that has a position closer to the camera than the near clipping plane won't be rendered. In addition to that, anything farther than the far clipping plane won't be rendered. The second type of cameras is the orthographic camera. An orthographic camera is used to render 2D scenes because depth doesn't count in this case. I'll make a comparison between the two types of cameras in just a second, but let's continue with the components of an orthographic camera. An orthographic camera is composed of 6 values. The first 4 are the left, right, top and bottom edges or limits of what can a camera picture out of the scene, and the last 2 are the near and far clipping planes, which I've already talked about. Here is an example to better understand the difference between a perspective and an orthographic camera. Notice in the case of the perspective camera, the size of the ball changes depending on how far the ball is from the camera. The closer the ball is to the camera, the bigger it looks, and vice versa. On the other hand, the ball maintains the same size no matter how close or far it gets when it comes to an orthographic camera, because depth doesn't matter in this case. Now back to the code. Let's create our scene and then the camera by instantiating the perspective camera class, which constructor takes 4 arguments, each representing one of the properties that we've talked about earlier. Field of view, it depends on what you're working on, but as far as I've seen, usually you'll be fine with a value between 40 and 80. Aspect, its value is going to be the width of the window divided by its height, since our canvas here takes the size of the window. Near and far clipping planes, will set them to 0.1 and 1000 respectively. That done, we need to link the scene with the camera using the render method from the renderer and set the scene and the camera instances as arguments. As you can see, the scene is empty because we haven't added anything yet, so let's add an axis helper, and as its name suggests, the helper is just a tool that serves as a guide. It merely introduces the 3D coordinate system I've talked about earlier into the scene. 5 here represents the length of the axis. And now that we prepared the axis helper, we need to add it to the scene using the add method. So we still can't see anything, and that's because the camera is set to the point with the coordinates 0, 0, 0 by default, and it looks at that same point. Therefore, to see the helper we need to move the camera, so let's do that. I'll pull the camera back by setting the value of its Z position to 5. And there we go, we got the helper displayed in our scene. Again, we can change the length of the axis by changing the value of this argument. Notice that our coordinate system has only 2 axes while it should have 3, and that's because of the camera position. So to be able to see the Z axis, which is the missing one, we need to change the camera's X or Y value. And as we move the camera upside, now we can see all the 3 axes. By the way, we can change the position of the camera or any element in the scene with one single line by calling the set method. The first argument refers to the X-axis, the second one refers to the y-axis, and the third refers to the z-axis. Now let's add a box to the scene, and I won't explain the steps right now as there is an entire section dedicated to that subject. We got our box, now we can carry out geometric transformations to it. An example of a geometric transformation is rotation, so here we'll perform a 5 radians rotation on the x and y axis. As you may know, an animation is actually a sequence of transformations that occur over time. Therefore, to animate this box, we need to apply the rotation in an automatic manner over time. So what we are going to do is to create a function, let's call it animate, then we'll put the rotation code and update it in a way that the value of the rotation gets increased 60 times per second. So every second we are going to rotate the cube by 0.01 radians on the x and y axis. That done, we need to pass animate as an argument to the setAnimationLoop method. Bear in mind that we can control the speed of the animation using the time argument to set the value of the rotation. We can add mobility to the camera in order to see elements of the scene from different angles using the mouse buttons. To do that, we need to import the orbit control module. Then we need to create an instance of the orbit control class and pass the camera and the renderer DOM element as arguments. Then we need to make sure to call the update method every time we change the position of the camera. This is very important. And there we go, now we are able to rotate the camera around by holding the left mouse button, and we can move it forward and backward using the mouse wheel, and also move it up and down, left and right by holding the right mouse button. The creation of an element in Three.js happens in 3 phases. The first one is the creation of the geometry or the skeleton of the 3D shape we want to add to the scene. The second phase is the creation of the material. It is basically the skin or the cover of the shape. There are a few materials available to use, but you need to choose carefully because some of them require more resources than the other materials since they have more features and are built in with more demanding algorithms. The third step is to cover the geometry with the material. So enough with theory, and let's get back to the code editor. In this block of code that we typed to create the box, the first line represents the first phase. We have an instance of the box geometry class, which you can tell by the name, it's a box skeleton. Keep in mind that the constructor takes a few arguments, like the width, height, and width and height segments. We'll get back to them later on. The second line represents the second phase. We have an instance of the mesh basic material, which is not the less resources demanding one of the materials, but it doesn't require light to appear on the scene. And as you see, we have a configuration object that contains a color property, which obviously represents the color of the material. The third line represents the third phase, which is the fusion of the geometry in the material. The result of this combination is a mesh. A mesh in the 3D world is an object. It could be a cube, a circle, or a character created using a 3D software. The fourth line you should be familiar with by now. It adds the mesh to the scene. That said, Three.js has more geometries that we can create, not only boxes, so let's add some of them. But before we do that, let's change the field of view and the position of the camera. That done, let's create a plane, for example. To do that, we need to create an instance of the plane geometry and pass the width and height of the plane as arguments. Now let's create a material, merge it with the geometry into a mesh, and then add it to the scene. As you can see, we got our plane displayed, but it looks like a wall. Instead, to see how it should actually look, we can add a helper. In this case, we are going to add a grid helper. We can pass a value to the constructor to increase the surface of the grid. We can also pass a second argument to the constructor to divide the grid into smaller squares if needed. We actually don't need that in this tutorial, so I'll get rid of it. So to make the plane match the grid we've just created, we need to rotate it. To do that, we can set the following value to the rotation X property. And there we go, we have our plane in the right place, but notice that looking at it from behind makes it disappear. To change that, we need to add the side property to the material and set its value to 3 double side. Now let's add another shape, and this time we are going to add a sphere. To do that, we are going to create an instance of the sphere geometry class and pass the radius as an argument. The rest is pretty much the same. We got our sphere in the scene, but if you look closer, you can see that it is not perfectly rounded. Actually, to clearly see that, we need to display the shape of the sphere in its skeleton form. To do that, we need to add another property to the material, which is wireframe, and set its value to true. As you see, the sphere is constructed from lines, points, and triangles, same as literally anything in 3D. Furthermore, the quality of the mesh depends on the number of the faces created out of these entities. That said, let's try to reduce the number of the width and height segments. The sphere looks way less rounded as a result of the reduction of the segments. On the other hand, if we try to increase the number of the segments, the sphere now looks perfect. Again, these are not the only geometries we can create, so make sure to check out the documentation for the other possibilities. As I said earlier, we used the mesh basic material for the meshes because that will make them appear without having to add a light source to the scene. But now let's try to use another material and let's see how the sphere will look like. As you see, the sphere is covered in black color since we have not yet added a light source to the scene, and that's how things work in real life actually. You won't be able to see anything if there is no light. The same thing goes for some of the other materials like the mesh standard material and the mesh Lambert material. They need light to show up, so again make sure to check the documentation to know the full list of the materials and their characteristics. We can't speak about meshes without mentioning how to position them, and we do that the same way we did with the camera, so we either set a value to X, Y, and Z each on its own, or change them all at the same time using the set method. Debugging and playing with values to get the perfect position of an element or its color, for instance, could take a lot of time, and a very common solution to that is to utilize a small-sized interface only for that purpose. We can create such a solution manually, but there are people who have already thought about the subject and they made an open source interface that is very popular among developers who work with Three.js. The module's name is dat.gui, and to install it we need to stop parcel first by hitting Ctrl+C and then type the following command: npm install dat.gui and restart parcel again when the installation is done. Now we need to import everything from the module, then create an instance of the GUI class. Now say we want to change the color of the sphere by having a color palette on top of our canvas. To do that we need to create an object that will hold the interface elements, the color of the sphere in this case. Then to add the color palette we need to call the addColor method with the options object set as first argument and the key of the element as a second argument, and make sure it is set as a string. The next thing we need to do is call the onChange method and set a callback function in which we specify what has to be done every time we change the color on the interface. In this example we want to change the color of the sphere. Color.set here is the method to change the sphere color, and the variable e contains the colors code gotten from the color palette. Now let's test this out. And there we go. The GUI has different type of elements, so we can add a checkbox, for example, to show the mesh in its wireframe mode when it's checked. To do that, let's add a property to the options object. This time we need to call add instead of addColor and pass the options object in the property key as arguments, then call the onChange method to change the value of the wireframe property that belongs to the material of the sphere. E here is set to true if the checkbox is checked and false if not. Let's add another example. This time say we want to make the sphere bounce and we want to have a slider to control the bouncing speed. Let's start by creating a couple of variables. One of them represents the speed of the animation. Then within the animate function we need to have the following logic which is needed to make the ball bounce. We have the animation working as intended. Now we need to add the animation speed controller. To do that, we'll get rid of this variable and recreate it as a property in the options object. Then we need to call the add method like we did earlier, but now we are going to add a couple of additional arguments. The first one represents the minimum value, aka the minimum speed, and the second one represents the maximum value. Actually, we won't need to use onChange here. What we are going to do instead is to take the value directly from the options object like this. There are different types of light that we can use to illuminate our scene or parts of it, including the objects or meshes that belong to those parts, which end up with them casting shadows over some of the other objects. In this tutorial we are going to discover three types of light. The first one is the ambient light. Ambient light is the light that comes from the environment. It is the indirect result of other sources of light. An example of that is the daylight in your room. The second type is directional light. The best example of a directional light is the sunlight. It has a source that is so big and so far, which in result covers all the space with parallel rays of light. The third type is spotlight. This source emits the light in a form of a cone. The farther the light source is from the surface that receives the light, the bigger becomes the cone radius. So to add an ambient light we just simply need to create an instance of the ambient light class, pass the color of the light as an argument, and then add it to the scene. Looking at the result though, nothing has changed, and that's because of the mesh's materials. If you remember, we created these elements using the mesh basic material, which is not affected by light. That said, we need to use another material. I'm not sure, but I think every other material is affected by light. However, they have different algorithms, which make some of them reliant on more resources than the others in order to make them cast smoother shadows and more realistic reflections. Having said that, let's change the material of the plane in the sphere to the mesh standard material and see what will happen. As you can see, the sphere and the plane colors look darker because we used a dark color for the ambient light. On the other hand, the cube remains as it is because we didn't change its material. Now, to add the directional light, we need to create an instance of the directional light class and pass the color and the intensity of the light as arguments to the constructor. The scene now looks brighter, and notice how the light affects the sphere with shading. Working with lights can be a bit tricky. Thankfully, Three.js provides helpers to help you achieve the best result with whatever type of light you have in your scene. That said, to add a directional light helper, we need to create an instance of the directional light helper class and pass the directional light we've created as an argument to the helper's constructor method. And there, right on the top of the cube, is the location of the helper. It's a square that indicates the direction of the light. Now, same as any other elements in the scene, we can change the position of the light source in order to change its direction, and therefore change the direction of the shadows, which I'll get into in a second. We can change the size of the helper square by setting a second argument to the constructor. And there we go, we got a bigger square for the helper. In addition, you can see how changing the light source position has affected the sphere. Now that we are done with adding light, it's time to add shadows. Shadows in Three.js are not enabled by default, so to enable them we need to set the value of the shadow map enabled property of the renderer to true. Then we need to manually set if an object receives or casts shadows. The plane here receives the shadows emitted by the sphere being in front of the light source. The sphere, on the other hand, casts a shadow by being in front of the light source. The directional light casts shadows. After all, it is the main factor of the shadow's creation. As you see, we got the shadow, but it doesn't look natural as it has a missing part, and that's because of the shadow camera. Actually, shadows in Three.js use cameras internally, which are the same as those we've talked about earlier. The role of a shadow's camera is to delimit where to render the shadows. That said, each type of light has a specific type of camera for its shadows. Directional light, for instance, uses an orthographic camera. Furthermore, to visualize the space that the shadow's camera marks for the shadows to be rendered on, we can use another helper. This one is an instance of the camera helper class, and it takes the camera of the shadow that belongs to our directional light as an argument. As you can see, now we have 4 orange segments that go from the camera through the plane. The square formed by these segments is the only surface on which the cast shadow can be rendered. So to increase the size of that surface, we need to move these segments away from each other. In this case, we need to push only the 2 bottom segments, and to do that, we need to update the position of the bottom side of the shadow's camera. Back to the code, we need to type the following line. And now that we shifted the bottom side of the camera, we created enough space for the sphere's shadow to appear. That's it for the directional light. Now let's move on to the third type of light, which is the spotlight. To create a spotlight, we need to make an instance of the spotlight class and set the color of the light. And there we have our light right at the center of the plane. Again, working with lights, especially spotlight, can be a bit confusing, and that's why Three.js provides a helper for this one too. So first, let's reposition the source of our light, then create a spotlight helper. This white segment represents the direction of the light, and if you scroll back you'll see 4 other segments which represent the boundaries of the spot created by the light. I forgot to add shadow, so let's add it before I explain one property of this light. The shadow appears, but as you can see it looks pixelated and not realistic at all, and that's because of the light's angle. The angle of the light source is the factor on which depends the positioning of the 4 segments that define the spot created by the light. Having said that, after testing I came to conclusion that if the angle is too wide, the shadow gets pixelated. I'm not exactly sure though if this is common or it's a performance issue caused by my 11 years old computer, so I'd love to hear from you when you test it. So to solve this problem, all we need to do is to narrow the light's angle. That done, now we have a better and smoother shadow, not to mention the appearance of the spot border drawn by the spotlight helper. This type of light has a set of properties that we can play with to create different effects, and we'll use the GUI to better visualize the changes that we are going to do to our spotlight. Something important you have to bear in mind is that we have to update the helper by calling the update method every time we change the values of the light's properties. Angle, we've just seen the role of this property. Penumbra, basically this property adds a progressive blur effect to the edge of the spot. And then we have the intensity of the light. We can add fog in Three.js with 2 different methods. The first one is by creating an instance of the fog class, which constructor method takes 3 arguments. The first argument is the color, and the 2 others are the near and far limits of the space where the fog should be visible. So the further we get from 0 going backward, the denser the fog gets, and the same thing goes when we get further from 200 and forward. The second method of creating fog is by instantiating the fog xp2 class, which constructor takes 2 arguments. The first one is the color and the second is density. With this method, the density of the fog grows exponentially with the distance from the camera. Up until now we've had a black background, and we can change that by calling setClearColor from the renderer. Now what if we want to have an image as background instead? To do that I have prepared a couple of images in this folder that I'll cut from here and paste it in the src folder. I'm not sure if you remember, but I'll repeat it again. To better organize our project files, we need to put everything we may need in the src folder, and then Parcel will bundle any used asset from there and put it in the dest folder if it gets used in the project's code. Having said that, since I want Parcel to include the 2 images in the dist folder, we need to use the import directive like so. Now notice that once I hit save, a couple of image files are created, but with strange and unpredictable names. So how we'll be able to use these images in our code now? Do we need to copy and paste the names from the files manually? You might be asking. Well, the answer is no, because the path and the name of each one of the images is now stored in the stars and nebula constants, so we should use these two constants whenever we need to. Back to our main topic, to use an asset in Three.js we need to load it first. Each type of asset aka file has a matching loader. In our case we need to use the texture loader to load an image and then set it as a background to the scene, so let's do that. The first thing we need to do is to create an instance of the texture loader class. Then we need to call the load method on that instance and set the path and the name of the image as an argument, and that will create a texture object out of the image that we are going to set as a background to the scene. The background has been changed, but it looks 2D, and that has to be expected from a 2D image, but that actually can be changed because the scene is just a cube in reality. Therefore, it has 6 faces, and each can have its own background, so the overall background appears like a 3D world. To do that, we need to use another type of loader, which is the cube texture loader, and the load method here takes an array of image paths that each will serve as a texture to a face of the cube, aka the scene. And now let's take a look at our scene, and as you can see the left and right sides are textured with the nebula image while the rest of the faces are textured with the stars image. Let's create another cube and see how to set a background to its faces. So to add a texture to a cube or any other geometry, we need to load it using a loader, of course. We'll use the loader we created earlier here. Then we need to set it as a value to the map property within the material coupled with the cube. The texture is green because we have the color property set to the green color, so let's get rid of that. So that's how we can set an image as a texture to a cube or a sphere or any other geometry, because the nature of the geometry doesn't matter since we are working with the material, not the geometry itself. In addition to that, we can change the texture later by updating the map property of the mesh's material. Now all of the faces of the box are the same, but what if you want to have a different texture for each one of these faces? To do that, we need to create a material for every face, and each should have its own texture. So first, let's create an array containing 6 materials. Then we need to pass this array as a second argument to the constructor of the mesh instead of the box2material variable. In some cases, you may want the user to be able to select elements from the scene, and that's easily doable. In Three.js, there is what we call array caster. Array caster, as its name suggests, it emits an invisible ray that has a source and a destination. That said, every element in the scene that the ray goes through gets registered. In our case, we need to set the camera as the source and the mouse as the second end of the ray. So, before we get into the code, there is something we need to understand first. Generally speaking, in WebGL, the values of the axis start from -1 and end at 1, and these are called normalized values. They are relative to the real values. Here are some examples of normalized values. The top right corner coordinates in my case are 19, 20, and 0. The normalized values are 1 on the x-axis and 1 on the y-axis. The coordinates of the point at the middle of the left side of the x-axis are 480 and 0. The normalized values of these coordinates are -0.5 and 0. Now back to the code editor. The first step we are going to do is to create a 2D vector in which we are going to put the x and y values of the cursor position. The second step is to add an event listener to catch the position of the cursor. Then we will update the vector we've just created with the normalized values of the cursor's coordinates. eClient x is the value of the x position of the cursor. In window inner width is the width of the window, thus the width of the canvas. eClient y is the value of the y position of the cursor. In window inner height is the height of the window, thus the height of the canvas. The next step we need to do is create an instance of the raycaster class. Then within the animate function we need to set the two ends of the ray, which are the camera and the normalized mouse position, by calling the setFromCamera method from the raycaster. Next we are going to create a variable that will hold an object that is returned by the intersectObjects method. This object will contain any element from the scene that intersects with the ray. So now if we try to display the values of this object in the console, you see that its values get changed when we move the mouse around the scene, because it keeps touching different elements including the helpers. If we open one of these objects, here for example we have these three elements. The first one is a mesh, it could be the plane, the sphere, or maybe the box. The second one is a point, or maybe an entire axis of the grid helper, I'm not sure, and same thing for the third object. So you might be wondering, how are we going to be able to select the right object, especially if the scene contains a lot of meshes? Well, we have a lot of options, and some of them are the UUID, the name of the element or the ID. Three.js gives an ID automatically to each element we add to the scene, and it sets it as a property which key is ID. So first we need to get it and then do a loop over the intersects object. If an element has the ID we are looking for, we can change the color of that element, for example. Now let's use a name, so we need to set a name to an element first, then add a condition within that loop based on the names of the elements. In here we will rotate the box if it gets hovered. We have the ability to change the shape of a mesh, and that's by updating the position of the points that make up the geometry of that mesh. To better understand that, let's create a 10 by 10 plane. As you can see, without mentioning the width and height segments, this plane is composed of 4 points only. That said, same as what we've seen with the sphere, we can add segments to the geometry in order to have more points to compose the plane. Therefore, we'll be able to apply detailed transformations to it. A good example of that is applying a displacement effect to a land if you want to create a game, or maybe create animated waves, etc. By increasing the number of segments, now the plane is composed of hundreds of points and faces. Be careful though, because more segments mean more resource consumption. Now, in order to change the position of these points, we can use JavaScript code or use the Vertex shader. If you don't know what is a Vertex shader, you should definitely watch my previous video. In this tutorial, we are not going to use that method. I'm actually leaving that for another tutorial dedicated to shaders and GLSL. So what we are going to do instead is to use a few simple lines of JavaScript. The positions of all the points that form the geometry of a mesh are located in an array in the geometry attribute position property. Each set of 3 values starting from the first element of the array represents the x, y, and z values of a point. So here, for example, if we want to change the position of the first vertex of the plane, we need to change the first three values of this array. Now, every time I refresh the page, three random values are set as coordinates to that vertex. To change the z position of the last vertex, we need to change the value of the last element of the array. I've talked about animated waves earlier, and when we say animation, it means changing the coordinates of vertices, aka points, over time. That being said, to update the coordinates of the first vertex and the z value of the last vertex, as you may have guessed, we need to copy this logic and paste it within the animate function and do a few changes. You have to make sure to add this line. It is crucial for the animation to work, so bear this in mind when you try to create your own animation. I actually wasn't sure if I needed to add this section to this tutorial, but I ended up doing so because this is not supposed to be something you're required to learn as a beginner. However, you'll need it later on, especially that I'm going to make a tutorial on shaders and I'll refer to this section on it. Anyways, in this part we are going to learn two methods to add vertex and fragment shaders in Three.js. Again, watching my previous video is a must if you have no idea what they are. Having said that, let's create a geometry and then a material, and this time our material is going to be an instance of the shader material class. The constructor here takes an object as an argument that has two properties, vertex shader and fragment shader. The values are two variables that we'll create in just a second. The first variable vShader, or whatever you want to name it, is a string that contains the vertex shader code. I won't explain this shader code here because I will do a tutorial dedicated to this subject. The second variable is also a string that contains the fragment shader code, and that's it. The second method, which is very commonly used, is to create a couple of script tags for the vertex and fragment shaders. Each one of these tags should have a type, and usually you'll see developers setting these values to the attributes xShader/xVertex to the vertex shader script tag and xShader/xFragment to the fragment shader script tag. These values are not recognized by Parcel though, so if I save here, notice that I get an error message in the command line. To fix that, we need to change the types to something without special characters, vertex and fragment for example. Now, the last step we need to do is to set the content of these two script tags as values to the vertex shader and fragment shader properties within the material instead of the variables. So if we take a look at our scene now, we should have everything in order. We can import models that we create using a 3D modeling program such as Blender. To do that, we need to make sure we export the model in the right format, GLTF in this case, but we can also export as FBX or OBJ. Then we need to tell Parcel we are going to use this file, so it creates a copy in the dist folder. It's pretty much the same thing that we did earlier with the images, but with different syntax, as this type of files require different way to bundle. That being said, we need to create a variable that holds an instance of the URL class. The constructor method here takes two arguments, the path to the file in the src folder, of course, and this portion of code that I actually don't know what it does, but it is required to import our model file. Once saved, you see that a new GLB file has been created in the dist folder. That done, now we need to import a special Three.js loader to load this type of files. The next thing we need to do is to create an instance of the gltf loader and call the load method on it. Load takes two arguments. The first one is the path to the file, and the second is a callback function. Our model is now stored as a property within the gltf object, which key is seen. So what we are going to do is to simply take it out from that object and add it to the scene and position it the same way we did with every one of our meshes. The second argument of load is another function which tells about the progress of the loading process. We don't need it here, so we can set undefined instead. And the third argument is also a function that we can use to tell if an error occurs. And there we have it. Right now, the canvas in its current state is not responsive. As you see, resizing the window doesn't affect its size in any way. Another problem is that when I refresh the page, the canvas stays in that initial size, so if I close the inspector mode, you see that the canvas is still taking only 2/3 of the window and resizing doesn't do anything. To fix that, we need to add an event listener to catch any resize attempt on the window. Then within the callback function, we need to update the aspect property of the camera and make sure to call this method update projection matrix every time you update any property of the camera. We are calling it here because we are updating the value of the aspect every time we resize the window. Finally, we need to reset the size of the canvas. This method should be familiar to you because we have already used it at the beginning of the tutorial. And this is it for this tutorial. I hope I succeeded at helping you setting the first building block of knowledge of this amazing library. I know some of the concepts are quite a bit hard to understand for someone starting from zero. However, with time, practice, and patience, I'm pretty sure you'll be able to get a solid grasp of them. With that said, make sure to like and subscribe, and I will see you in the next video.